This is a video showing a high frequency sine wave with almost no distortion um, generated from a DC source. And you can see that the frequency is 72 kilohertz and it looks very clean. It's the cleanest sine wave I've ever generated so far from a 20 volt DC power supply. So how does the circuit work? I'm using a colpitts oscillator as shown by this diagram. And previously I had created a Wine bridge oscillator which used a series of here it is, with a series of RC filters, two cascaded RC bandpass filters, along with a gain regulating network, and an op amp. So why is the Colpitts oscillator better at generating, lower distortion, high frequency waves? Well, we have to understand how the Colpitts oscillator actually works first. So like when I first looked at this, I was like, cool, this is a common emitter amplifier, but why the common emitter amplifier gives a negative 180 phase shift, and what is this contraption down here? How is this, how is this a bandpass filter, and why is this loop gain? How does it equal 1? Because there's no mechanism to do gain control here. And also, how's the phase shift 0? Because this is a 180 phase shift. Does that mean this somehow generates a 180 phase shift as well? So how does this all work? And I had a lot of questions like that, which weren't really explained in the textbook. And it started mattering when I started picking components for the design because it just didn't make sense. So I just want to quickly go over what this oscillator actually is doing. Specifically, what is this filter here? Because it's a weird looking thing. And it's actually just drawn weird. Like what this filter really is what's up here. So you have basically an input voltage, in this case coming from this side, and it goes to a resistor to ground, and then an inductor, and then a a capacitor to ground, an inductor, another capacitor to ground here. And then what happens is the amplifier, right? This amplifier has input and output impedances, which both the input impedance is actually a resistor to ground because it's this network parallel to this, parallel to that, and the output impedance is actually this RC capacitors in series. So this filter actually looks like this on the LT-SPICE simulator. It looks like this. So there's some voltage source, and the filter looks like the series resistor, which is the output impedance of the common emitter amplifier. And then there's a capacitor to ground, the inductor and a capacitor to ground, which forms a LC tank. And there's this resistor to ground, which is the input impedance of the amplifier. And basically, this amplifier, what this filter does is it's actually not a bandpass filter. That's the surprising thing about this. A lot of textbooks will say that the Colpitts oscillator uses a bandpass filter, but it's not a bandpass filter. It's actually a low-pass filter. It's a second or third order low-pass filter, and it has a response curve that looks like this. So essentially, the attenuation starts going down, and then there is a resonance peak where what happens is the LC tank will slosh voltage against each other, and it causes a resonance voltage to give a slight peak, and then it attenuates sharply after that. Likewise, with the phase shift, it actually does not invert the phase, 180 degrees always at the resonance. It depends on these two resistors actually. And in fact, if you remove this resistor, the phase shift will approach 180 degrees as the frequency approaches infinity. But by adding the series resistor, this 1K, the phase shift will basically be boosted 180 degrees approximately at the resonance frequency, not exactly though, and then it approaches minus 270. So it's actually a low pass filter. So then, if it's a low pass filter, right, why are these frequencies not showing up? So if it's a low pass filter, why are low frequencies not coming through here, getting amplified, and then, getting added back up again? The reason is because even though the attenuation is smaller for like lower frequencies, the phase shift is not 180. So phase shift, they'll destructively interfere, and they don't get added up with the same factor in the loop. So the resonance frequency is actually not determined by the resonance peak. It's actually determined by when the 180 phase shift happens. So that's really what's causing a particular frequency to be selected by this filter. It's the phase shift, not the resonance. And so the next thing I want to talk about is where's the gain control? So when I did all my derivations and I calculated the resistor values and stuff like that, I ended up picking a gain of 20, right? And so there's nothing that really controls the gain because, there's no gain control network like the two diodes that I used for the Weinberg oscillator, which actually introduced a distortion because diodes have reverse recovery time. So when the wave, if the wave is too fast, like the frequency is too high, you can actually see this distortion as the wave drops to the forward bias voltage, and the diode takes time to shut off this reverse recovery, and it basically janks the wave a little bit at the turnoff voltage. And so how is gain controlled in the Weinberg oscillator? So the gain is controlled because even though the common emitter amplifier has a gain of approximately 20 in this setup, it's 1K divided by 47 ohms because the 150K is bypassed. This gain will decrease as the transistor approaches saturation and cutoff. So if you're approaching saturation and cutoff gently enough, it actually makes sure that the gain ends up lowering, because at saturation cutoff, it's exactly 0, the gain. And before saturation cutoff, it goes through a range of values. So it's not a discrete shutoff like the way that an op-amp would be. So therefore, it doesn't actually clip the rails very hard. It's got a gradual clip, where at some point, there's going to be some point where the gain is actually just 1 across the loop. And that's what's causing the gain control. It's actually using the gradual saturation and cutoff of the transistor to achieve this gain of 1. And lastly, I want to just talk about a few things that I encountered when building the circuit. So at first, my calculations ended up using a 50 ohm or like a 47 ohm unbypassed resistor. And so the reason why I chose to bias it this way is because, so let me just show you first. The reason why I chose to bias it this way is because when I plugged in the calculated input and output impedances to the common emitter amplifier into my simulation, so I plugged in the input impedance and the output impedance, the attenuation at the resonance peak was approximately 15 decibels. So, I thought about, okay, well, it's not going to be exactly at the resonance when it achieves a 180-degree phase shift. So, plus or minus 15 decibels, maybe a gain of 20 would achieve, what's needed. And so when I actually tried to build it this way, what happened is you can see that, hang on, let me auto it. You can see that there's a little bit of distortion at the top of the peak. And that's because when the gain is too sharp, it can actually slam into the supply rails at the very top, and it's not there's not a gradual enough of a roll off to the unified gain of 1. So then, by increasing the resistance in the emitter, the unbypass resistance, to 100, it fixed this problem. So now the wave is very smooth, and there's no distortions whatsoever at 71 kilohertz. So yeah, as you can see, the calculated frequency is supposed to be 55 kilohertz, but it fell to 71 because it's at 71 kilohertz that the components of my circuit achieves a phase shift of 0 and a gain of 1 at near saturation and cutoff for the transistor. Yeah, and then lastly, I also thought about what can cause this frequency shift, because even though it's quite accurate, like 55 kilohertz is not that different to 71 kilohertz. There are a few things here, right? So for example, the coupling capacitors, they also introduce a phase shift. So the phase shift introduced by those have to be offset by whatever phase shift is in the LC tank filter in order to achieve 180. And obviously, because I'm using like cheap Chinese components, these capacitors are not exactly as they're stated. When I measure the capacitances, this was supposed to be a 100 nanofarad, but it turns out to be 40 and 60. So, and the inductor, I can't even measure what that is. So, like, when you add up all these differences, it's pretty good. Like 55 kilohertz is pretty close to 71. Yeah, and that's it. So just one more time looking at the resulting wave. Clean sine wave, no distortion.